Hello, we're going to take a break in the series, the Cosmic Origins of Life series, but we will get back to it. So for Cosmic Origins of Life fans, next video will be part 2. But don't skip it, because these math videos, I'm told, are romantic date night material. Not quite sure who told me that, but I imagine they would be. Anyways, we're going to talk about the derivative of the sine of angle, and as you all know, that's equal to the cosine of angle, and that can be proven. That's best proven from calculus. You have an infinite series that would define the sine angle, and if you take the derivative of that infinite series, you will get the infinite series defined as defining the cosine of angle. That goes back to Euler. But I thought I'd have a little fun, and I want to see how this works out. If it doesn't, comment, and I'll either redo the video, or probably more likely pull it if it doesn't work out, or just maybe redo it at the end of my Cosmic Origins of Life series. So again, we're going to see if we can use geometry and trig to prove the derivative of the sine of angle is equal to cosine of angle. And I think that this I'm sure this has been done before, and if it has been, great, because it means I'm right. If it hasn't been, then you know, then that's a good question. Why hasn't it been? Maybe. We'll see how it goes. Let's take a circle. We have R1 and R2. Okay, not very well defined. And we have, in the case of R1, I have a vertical dotted line going down to the x-axis, forming a triangle. Okay, and in the case of R2, I also have a vertical dotted line going down, forming another triangle. Both these triangles have unit length 1. R equals 1, and we're only going to consider hypotenuses with length 1 in this, okay? Even when we have, it's going to get a little tricky, but we'll work our way through it. Note I also have from, wake up the screen there, from R2 going to the left, I have another dotted line, and I have something that forms a triangle that we're going to blow up to unit length 1. So don't worry about unit here, it's just unit length 1. Note something interesting, that the length of this vertical line is going to be the same as sine of angle 1 minus sine of angle 2, or sine of theta 1 minus sine of theta 2. Why? Well, it's going to be the difference of the vertical heights formed when R1 intersects the circle, vertical meaning from the x-axis, the vertical height of theta 1 minus the vertical height of theta, well, the vertical height of R1, where R1 intersects the circle, minus the vertical height of R2, where R2 intersects the circle. Or this height minus that height. Well, for a unit length of 1, that's just going to happen to be, since the sine of angle is the side opposite over the unit length of hypotenuse, okay, or the side opposite over the hypotenuse. The hypotenuse in both cases happens to be R, or unit length of 1. The sine of theta 1 is just going to be this vertical height, and the sine of theta 2 is going to be this vertical height, and the difference of the two will be this vertical height here, blown up here, okay? Now, that happens to be the sine of this angle here at unit length 1, okay, if the hypotenuse is unit length 1. And with any circle we draw, you're going to have to blow it up to unit length 1 for this to fit. Otherwise, we get bogged down in a whole bunch of algebraic stuff, and I just want to get to the concept. So this height is going to be sine of theta 1 minus sine of theta 2. Now, what happens as theta 1 goes to theta 2? Something very interesting happens. We now have, I've got to move it over here for a second, we now have a tangent line that forms. Okay, as the two mush together, we have a tangent line that forms that is tangent to the circle and at a right angle to the radius of the circle. Note something interesting here, that the absolute value of the slope of that is going to be d sine angle. Well, let's go back here to figure it out here. Sine of theta 1 minus sine of theta 2 is essentially delta sine angle, right? It's the change in the sine of angle. But as these two get closer and closer together, as theta 1 becomes theta 2, that's actually going to be d sine of angle at unit length 1. Well, in other words, the sine of this angle is going to be d sine of angle. And at unit length 1, this vertical height will be our d sine of angle. Okay, so as this triangle becomes infinitely small, the side opposite over the hypotenuse gets closer and closer to being d sine of angle. And if we take that infinitely small triangle and blow it up to unit length 1, sure enough, this vertical height here is going to be d sine of angle, and the absolute value of the slope of this tangent line is going to be d sine of angle. Okay, I've brought this over to here, and I now, let's see how much time I have. Okay, I'm making good time. I now have here's our angle theta. Here's comp theta. I'm going to call this comp theta because this is the y and the x axes are at 90 degrees to one another. So this is going to be comp theta. By the alternate interior angle theorem, this particular angle that is not marked between the radius and the dotted line is also going to be theta. And since this is at a right angle, this is going to be comp theta. Okay, so this is the measure of this angle between the dotted line and the tangent line that is dark is going to be the same measure as this angle between the radius and the y-axis, okay? And then theta, theta, comp theta, comp theta. All right. Going over here, I'm going to draw this a little better, except I forgot to put the theta here. Sorry about that. Theta, comp theta, theta, comp theta. Okay, notice that I brought my d sine of angle as unit equals 1, and I'm always making my unit equals 1 for clarity's sake. So this vertical height's going to be d sine of this angle here. But notice something interesting, that the d sine of this angle here, this angle is actually, this triangle here is exactly going to be similar to this triangle here, and at unit length 1 they're going to be entirely congruent. Okay, so this triangle here, if blown up to unit length 1 in both cases, they're going to be exactly congruent, and therefore this angle is going to be equivalent to this angle. And so the sine of this angle, meaning the side opposite over the hypotenuse, is going to be exactly d sine of theta. Okay, so sine of comp theta is going to be exactly equal to d sine of theta at unit length of 1 in this particular scenario. Okay. Now, what do I also know? I also note that the sine of comp theta would also be its side opposite over hypotenuse. Okay, which at unit length 1 will be exactly this dotted line over this particular, at unit length 1, this would be exactly this dotted line. Note something interesting, that since this dotted line is parallel to this dotted line, okay, and since they're of the same length, note that sine of comp theta is exactly going to be equal to cosine of theta at unit length 1, which is actually true for complementary angles no matter what. We didn't even, that the cosine of an angle is going to be equal to the sine of its complement, okay? Well, cosine of angle is equal to sine of comp angle. Sine of comp angle is equal to d sine of at theta at unit. Therefore, by the transitive property, the cosine of theta is equal to the d sine of theta at unit. And yeah, so there we go. We've proven it geometrically. Now, if you work it out yourself, you're going to have to go and work it out with a lot of algebra that I don't have time to do within the 10-minute limit. But we're assuming here for any kind of a ratio sine or cosine, we're just going to assume unit length 1. And we're going to build that in as an adjustment. So bottom line is going back here, just going back here, yeah, this is going to be the same, where do we have it? Well, bottom line is we've proven that through geometry that the derivative of the derivative of the sine of angle is equal to the cosine of angle. And I think I'm entitled to a nice break. We're going to do part 2 of the Cosmic Origins of Life series, and we're going to have fun.